compartment C. Uh-oh. He told me recently he joined a lattice cult. And he also told me if I fall asleep during his talk, which might happen, that it wouldn't be any different than when he's trying to teach his kids something.
That's right.
Let's see what happens. You got another chair over here you can pull back. There's 2 more chairs you want to front forward. All right. So take it away.
Okay. Yeah, well, thanks everybody for being here. Yeah, so I'll talk about some research that I've done for several years now. This program sort of started while I was a PhD student in South Carolina on using the large NC limit of QCD in order to constrain nuclear forces in effective field theory, as well as currents relevant for PSM physics. And so, why is that not working now?
You have to click on the slide again.
Huh. Okay.
Oh, the computer's just not working.
Yeah. Okay, hold on. I'm gonna quit. Keep that like that. Well, no, it's done. It's still sharing. No.
You might have to share your whole screen instead of just sharing.
Let's try that. Okay, that'll work.
And you have a mouse.
Yeah, better. Okay, yeah. So, I've been spending a lot of time talking to my nephew, who has become obsessed with Star Wars, so that influence has trickled into this talk. Right. And so, we know that throughout the universe, there is more matter than antimatter. One of the conditions in order to generate this asymmetry is that there is CP violation in excess of what the standard model can provide. Right? It's because the baryon density, if you take the difference of the baryon and antibaryon density and normalize this to the photon density in the universe, you have something like order 10 to the minus 10 instead of 0. We also know that from neutrino oscillations that neutrinos are massive. And one way to accomplish this would be to give the neutrino a Majorana mass. If we see this type of process, if neutrinos are Majorana, then neutrinoless double beta decay, which is a process where you convert 2 neutrons to 2 protons with the emission of 2 electrons, this type of process would be what is often called in the literature a smoking gun signature. We also know that the universe has a substantial chunk of dark matter, right? And these are all questions, we just don't know the nature of dark matter, and these are all questions that the standard model doesn't answer. But these all rely on low energy nuclear physics or hadronic systems to study experimentally. Now, this last one is more of a rhetorical question. Why is low energy hadronic and nuclear physics so hard to describe in terms of fundamental particles, and specifically quarks? And so we have that in the region, typical of hadronic scales, where momenta are order GeV or smaller, QCD becomes non-perturbative, and so you have to turn to tools other than perturbation theory to describe low energy processes. And so now we have the first episode in the franchise, A New Hope, where we're introduced to our hero known as effective field theory. And so effective field theory, since it was sort of initiated by Weinberg, provides what we like to call a model-independent tool to connect high energy scales down to low energy scales, where QCD would be non-perturbative. At every, so you can start from some UV completion of the standard model, and then at some scale of new physics, integrate out heavy particles, match onto the standard model plus higher dimensional operators. Through a process of running through the renormalization group and integrating out heavy degrees of freedom, you can go through several series of theories where at each stage you have some sort of Lagrangian describing composed of local operators with some sort of undetermined coefficient, and these have a power series expansion of your sort of characteristic momentum divided by whatever the breakdown scale is, right? So then when you get to sort of the GeV scale, as I said, this is where you need non-perturbative QCD input into the low energy EFTs describing mesons and baryons. And so the ideal case is that all of everything in this theory should be fixed by lattice QCD input. And then to describe, say, many body nuclear systems, you can turn these things over to people working in, say, ab initio methods. And so sort of the poster child of EFTs would be chiral perturbation theory for mesons. So if you have, let's say, two light flavors, for instance, where you would have an up and a down quark in the massless limit or the chiral limit, this Lagrangian has this left-right chiral symmetry. It's broken explicitly by the quark masses, but these are small relative to, say, the QCD scale parameter, for instance. But we know from phenomenology that the pions are relatively light compared to other mesons. They're pseudo-scalar particles. They don't have a positive period partner. And so this gives some sort of phenomenological indication that chiral symmetry is spontaneously broken. And in particular, the pattern is that this left times right group is broken down to the vector subgroup. And so Weinberg realized you could realize this type of symmetry breaking pattern non-linearly. And then this was formalized by Callan, Coleman, Wess, and Zumino in order to write down an exponential parameterization containing the pion fields. And you can just construct every single operator that is invariant under this particular chiral group, but has a ground state that's only invariant under the vector subgroup. And so you can also extend this to nucleons, right? So this is really just a bird's eye view of what chi-pt for nucleons is, right? So you put your nucleons, your fermions into fundamental representation of the isospin subgroup. This is the vector subgroup I just mentioned. And you can play the same game of this small u would be the unitary square root of the big U that we just saw on the last slide. And you can specify the transformation properties of all of these building blocks under chiral transformations. And this would be essentially the unique leading order thing you can write down. You can extend this process to a few nucleon systems where now we refer to this as chiral effective field theory. So you have all of the single meson or few meson contributions, the single baryon contributions, and then you pick up all of these little local contact terms. And this has been worked out to like fifth order in the chiral expansion, and where say all of these contact operators are typically fit to scattering data, and then this is fed into say quantum Monte Carlo calculations or couple cluster calculations in order to calculate the properties of medium mass to heavy nuclei. Now, in spirit of effective field theory, where EFTs are supposed to make your life easier, you can focus on few body systems where sort of the typical momentum scale of the nucleons would be much less than the pion mass, in which case you can integrate out all the pion exchanges and just describe nuclear physics in terms of contact operators that are particularly fine-tuned in order to describe, say, the large scattering links that you would see in the two-nucleon system. But the details of that are not super important. The most important aspect of this is that all of these low energy coefficients are a priori undetermined. And so you need to, you can do perturbation theory and figure out the infinite parts of these in some particular renormalization scheme, but we don't, we need to fix the finite parts of the LHCs. On one hand, you can fit these to experimental data, but then you sort of cut yourself off at the knees in order to search for BSM effects in precision physics. Or in other cases where you may have some type of forbidden process like neutrinoless double beta decay, there is just no data, right? So we could match the lattice QCD. In the case of mesons, this is a very viable option. Single baryon quantities, this is feasible. Few nucleon systems are pending what Andre will provide, hopefully soon. And so in the meantime, we can actually turn our focus towards the large NC limit of QCD to get sometimes quantitative, a lot of times qualitative constraints. And so Tufte realized this would have been, I think, the same year that he and Veltman figured out how to use dimensional regularization in order to normalize gauge theories. So he had a very productive year. But if you look at the one loop beta function in QCD, you pick up this factor of NC in the first term. And so Tufte realized that he could take the large NC limit if he rescales the ordinary QCD coupling such that it goes like 1 over the square root of it. So this G hat is some order 1 quantity fixed in a large N limit. And when you do this, you end up with a very similar beta function where this second term proportional to the number of flavors vanishes, but you still have an asymptotically free theory. And also you end up with a QCD scale parameter that is order 1 with respect to NC. And when you do this, QCD turns into a topological expansion. And what I mean by that is that you will, the whole theory will be dominated by Feynman diagrams where you just have gluons along a boundary. But then if you include a quark line, you end up with all order NC graphs dressed essentially to all orders with gluons that you can draw on the plane. So there is, it is, you would hope that this would turn QCD into like a solvable model, but unfortunately, it's still impossible to sum up all order NC diagrams with a single quark running along the boundary of the diagram. But
That was another question.
yeah,
Sorry, can you go back?
So by the statement in the bottom, does that mean these diagrams on the right, the one on the left goes as NC squared?
No, so this would be a diagram like only with glue bonds in it.
Okay.
Right. So if you just draw a circle of a glue bond. So from counting this and counting the number of basically closed color traces, which is represented by these sort of double line diagrams, you can figure out that you have say 1, 2, 3, 4 factors of G and 1, 2, 3 independent sums over the color, and all that brings you to an order NC.
Where did that fourth one come? You said 1, 2, 3, 4.
So you have the vertex in the middle, the 3 gluon vertex, and the 3 quark gluon couplings.
Thank you.
And so, shortly after Tuft published this work, there was a lot of work on mesons, where you can actually get several interesting quantitative properties, but a few qualitative observations are just that you have an infinite number of stable mesons. Witten and Coleman realized that, or they've actually provided a proof that chiral symmetry is spontaneously broken in the large NC limit. But the chiral U1A anomaly vanishes in the large NC limit, which means that instead of having SUN cross SUN being broken down to the vector subgroup, you actually have the full UN groups. And so the nonlinear realization of chiral symmetry now picks up this extra phase that you can associate with the eta prime in the 3-flavor case. In the 2-flavor case, this would be some linear combination of the eta and the eta prime. Furthermore, you can show that the mesons are all weakly interacting. So every 3 meson vertex would scale as 1 over the square root of n. 4 meson is 1 over n. And you can repeat this ad nauseum. Baryons, on the other hand, are considerably more complex because they are fermions. And so to have a totally anti-symmetric wave function, you have to have NC quarks totally anti-symmetrized in their color indices. As a result, the baryon mass will be on the order of n. And then from just combinatorics, you can conclude that a meson scattering off of a baryon should scale like order 1, while the 2-baryon interaction shown here should be order NC. But then we have sort of a standalone movie of 1-baryon properties, right? So since the pion nucleon scattering amplitude from combinatoric should be order 1, we should this imposes pretty strong constraints on the form of the meson nucleon couplings, right? So in particular, the pion couples to the nucleon through the axial vector current, right? You can insert this on any of the NC lines inside of the nucleon. And so you would not even think that this matrix element is on the order of NC. Now at tree level, if you calculate the pion nucleon amplitude, you get something that looks like it is order NC squared. And this is just an unacceptable situation. So we need to sort of come up with a way to ensure that this commutator of axial vector current operators will scale as 1 over NC squared. Right? And this implies that, yes, go ahead.
Sorry. I thought, remember, the pion nucleon coupling is the square root of NC, right? Not NC, so.
Well, so, yeah, so the axial the axial current will be order NC, sort of just glossed by this. The decay constant will go as the square root of n. Right? So then, if you look at this factor, there is an n
And there.
floating
that's
around.
Where, right.
Yeah. Yeah. So in order to sort of satisfy this relation for this commutator, it turns out you have to have an infinite number of degenerate baryon states in the large N limit, right? So if you only include an intermediate nucleon propagating here, all of these commutators will just look like, say, the commutator of Pauli matrices, right? We know this is not zero. It just gives you another Pauli matrix. And so this means you have to have some other states propagating here that will cancel, right? So in particular, if you have pion scattering off of a nucleon in the P wave, it tells you that the delta resonance should be stable and degenerate with the nucleon in the large N limit. And in particular, this commutator tells you that the baryons will fill out irreducible representations of SU4 in the two flavor case. And so this follows from the structure of contracted algebras that Wigner figured out a long time ago. Okay. And so you can work with these types of generators, but it turns out that gets sort of difficult to work with. But you can instead just use the basis of SU4 generators. So this is what they, a spin generator, an isospin generator, and a combined generator, where they have single baryon matrix elements that look like this. So if you insert this G operator here, it is a spin 1, isospin 1 operator. So if you normalize this to NC, then it's an order 1 matrix element, while both the spin and the isospin matrix elements will be on the order of 1 over NC. Right? And so this basis is, it forms a complete orthogonal set, so you can expand to any QCD operator in terms of this basis. So this would be, say, a QCD operator containing M quark bilinears. You pick up an overall factor of NC to the M, and then you contract all of your indices in order to match whatever transformation properties you have on the left-hand side. So in the context of an EFT, what you can do is, so the EFT operators are constructed in a way that explicitly reproduces the symmetries of these operators. So you take the scaling that you obtain from the right-hand side and map this onto the LECs of your EFT. And so we did this for several things, in particular neutrinoless double beta decay, more recently CP violating pion nucleon couplings, and we'll cover both of those in particular. But just to see how this plays out, you can look at a very simple example of the baryon mass. So in the absence of isospin breaking, this is just an isospin 0, J equals 0 operator. And so at leading order, you just get this factor of NC times something proportional to the identity. And at 1 over n squared, you get something proportional to J squared. So J, this would just be, give you the ordinary J times J plus 1. And so what you can conclude from this is that at leading order in large N, the nucleon and the delta are degenerate, and then their mass splittings are on the order of 10% relative to leading order. And so we can now play this game for the quark chromo EDM and magnetic dipole moment. elements. So in particular, these operators are the chromomagnetic dipole and the chromo-EDM are related by a chiral symmetry transformation. And these get mapped onto a pion nucleon Lagrangian in this way. There are a lot of formulas here. But what you have are at lowest order, two independent operators. The notation here always gets me a little confused. I blame Andre for that because he was involved in this work. So G bar 1 would be an isoscalar operator, while G bar 0 would be an isovector operator. Right. And so you can relate these coefficients to the chromo-EDMs of the quarks and these sigma terms, right? So the sigmas without the subscripts are sort of ordinary sigma terms in QCD, while we also have these matrix elements of chromomagnetic operators. Right? And so what we did recently, and well, this should appear in the next few weeks, is you can figure out that the isoscalar term is going to be the same thing as the mass operator, and so this G bar 1 should scale as NC. We also have that the isovector operator will be I equal 1 and j equals 0, so you get a 1 over NC suppressed correction. And so you can combine this with an extraction of the twist 3 distribution of the nucleon to actually get quantitative results for these sort of magnetic sigma terms. Right? In particular, we find that, of course, the isoscalar contribution is about 3 times larger than the isovector contribution, consistent with the scaling. Moreover, this disagrees pretty strongly with an existing determination of these sigma terms by Chenye Seng. In particular, the sizes of these sigma terms are reversed. And this is related to the fact, basically, the treatment of these operators. In particular, this previous work tried to use the spin flavor constraints for operators not containing the gluon field strength tensor, whereas, as far as we know, this is the first explicit constraint for these operators containing the gluon from spin flavor. Okay, so now we move to the two-nucleon system, right? So you can define a two-nucleon potential in this context as just the matrix element of the QCD Hamiltonian, and so you do the same thing that we just did in the single baryon sector. You expand the Hamiltonian in some series of operators with indices contracted in a particular way. But now the coefficients of the expansion have some momentum dependence, right? And you can so P minus, for instance, would be the difference of the outgoing and incoming relative momenta, while P plus would be the sum. And in the T channel, there's an argument to be made that P plus is 1 over n suppressed relative to P minus. This comes from factors of the nucleon mass from taking a non-relativistic limit. But in the U channel, these scalings just get flipped around. And then you can determine sort of the scaling of all of these potentials by looking at the scaling of individual matrix elements between nucleon states of this Hamiltonian. Right? So if you do this, right, then you can look at the central potential, right? So this first term would look something just like an identity times an identity operator. You get something that looks like S1.S2, I1.I2, and G1.G2. Right. So if you remember, G1 scales as NC, while S and I both are order 1 for physical baryons. And what you end up seeing is that the broken up by their isospin structure, you have where did it go? Yeah, so the G.G operator will be NC, and this first coefficient will also be on the order of NC, while the rest are suppressed. And now this last operator and the first operator are actually related by Fiert's identities in such a way that this potential is manifestly invariant under Wigner SU4 leading order in large N. And so you can compare these constraints to phenomenological potentials as well as chiral potentials, and just looking at, if you look at the spin and isospin numbers of these different meson couplings, then the large N expectations are relatively, fulfilled relatively at like the level of 10%. And so we also we extended this to look at isospin breaking in the two nucleon interactions, and this is something that Jerry actually worked out a lot in the 90s and 2000s. And so there are sort of 4 classes of charge symmetry in the nuclear force. You have symmetric interactions, terms that break charge independence, terms that break charge symmetry, and then this last class also breaks charge symmetry, but they only occur in P wave or higher, and so they're going to be suppressed in an EFT context. But what we have all these scalings that are relatively reflected in both phenomenological and chiral potentials. But now we want to apply this to neutrinoless double beta decay. Right? So, as I mentioned earlier, this would be explicit proof that the neutrino is Majorana, and it would also shed some light on the baryon asymmetry of the universe. Right? But as of within the last decade, the nuclear matrix elements for this process have been all over the place, so it's obviously imperative to bring some agreement to the field. But, and this again, Andre had a bit to do with this as well, the light-Majorana exchange mechanism. Right? So one way to generate this process in a low-energy EFT is to exchange a Majorana neutrino between 2 incoming neutrons, and then you get 2 outgoing protons with 2 electrons. And in both a pionless EFT scenario and chiral EFT scenario, where you have pion exchange to all orders, you end up with a logarithmic cutoff dependence in the amplitude for this process. And this is really coming from a diagram like this, where you have essentially something that looks like a Coulomb exchange between 2 nucleons dressed by these zero derivative contact interactions. And so in the pionless theory, we know how to renormalize this in perturbation theory. Right? You add another contact operator to absorb the logarithmic dependence on the cutoff, or 1 over epsilon pole in dimensional regularization. Okay. But then it was also realized that chiral symmetry relates this G nu to operators describing charge independence breaking. In particular, you have basically the tensor product of two left-handed currents for neutrinoless double beta decay, where in charge independence breaking scattering, you pick up contributions that have left times left operators, right times right, and left times right. And so this the chiral symmetry relates G nu in particular to this coefficient C1, describing this type of operator. And so using by approximating, right, well, let me back up and say what we're doing here. This combination C1 plus C2 is accessible from scattering data because it starts with no pions in the interaction. However, the difference C1 minus C2 is sensitive to two-nucleon multi-pion interactions, and so it's really not, you can't extract it from anything currently. And so in order to estimate the impact of this LEC on neutrinoless double beta decay matrix elements, Vincenzo and company approximated it as the average of C1 and C2. So the piece that is accessible from CIB scattering data, right? And you can see, say, in helium-6 to beryllium-6 transitions, the open diamonds would be the matrix element without the contact term, while the filled diamonds would be with it. And you can see that, for helium-6, helium-8, and calcium-48, this contact term leads to a pretty noticeable change in the matrix element. And so what we did, so we started from basically a complete basis of operators and spent a lot of time using Peirce relations in order to figure out that the difference of these CIB LECs should be 1 over n suppressed with respect to the sum. And so this gives a justification for taking G nu to be the average of this. But if we actually fit this combination to a scattering length in the two-nucleon system, we can sort of use the large NC estimate to disentangle C1 and C2, right? Which would give C1 or G nu, up to 30% corrections roughly. And so it's worth noting that this was in agreement with an analysis based on a dispersive approach in order to match the operator product expansion in perturbative QCD to the low energy chiral effective field theory. So it is worth noting that also here we would expect roughly a 30% uncertainty on this, while the uncertainty in this relation is about 50%. Okay, so the last sort of few minutes, I want to bring back up the delta, right? So all of the these large N constraints for neutrinoless double beta decay, as well as other constraints available in the literature for the NN force, have been based on just looking at the spin isospin structure of operators without actually considering the impact of the delta resonance. But I told you earlier that the delta resonance has to be in the theory for it to be consistent with large N expectations. And in particular, this has been shown through brute force that to get the correct scaling of the NN interaction, you have to have propagating delta degrees of freedom inside of these loops. So we're left with the question of why would we expect any of these large N constraints that we derived previously to actually work. And so, well, yeah. So since we know that the nucleon and the delta are degenerate at leading order in large N, and they transform in particular as a representation of SU4, we can take a Lagrangian written in terms of SU4 valued fields, right? And these fields, there are only two independent operators you can write down. One looks sort of like a number operator, and then one picks up some other SU4 contractions. But they can be decomposed pretty nicely into delta nucleon fields, where all of these spin and isospin pairs are completely symmetrized. And if you just plug in this form into this Lagrangian, and just continue trying to simplify things, use some Peirce rearrangements, what you can do is find that the coupling between two baryons with a given spin and a given isospin after a partial wave decomposition, in particular in the S wave, because these are zero derivative operators, have this additional symmetry. In particular, it's a Z2 symmetry that in this paper we've referred to as flip symmetry. And so this seems to be respected in most even partial wave couplings, but it is broken in odd partial waves. And so, but if you look at the explicit forms of these coefficients, the B tilde from the last slide typically comes with a small coefficient, right? It's normally suppressed by 1/27th, sometimes 1/3, which, if we're counting NC equal to 3 is large, then 1/3 is also a small number. And this sort of suggests that we can treat B tilde as being somewhat close to 0, in which case the nucleon, two nucleon states and the delta states will completely decouple, since their coupling is driven only by this B tilde. Also in that case, the two nucleon system couples in exactly the same way as the delta system, with in all spin and isospin channels. And this leads to an even larger symmetry, in particular that the nucleon and the delta will form a the fundamental irreducible representation of SU20.
But B tilde over 27 is small. Why should B tilde be small?
So this is supported by some previous lattice calculations that we likely can't trust right now.
Okay.
But the next slide, I'll maybe give another example that will motivate this. So I've mostly been talking about systems where we just have the up and the down quark, but we can include sort of the lowest hanging fruit from strangeness, right? And so if you try to put in a 2 omega system into the problem, you can extend the Lagrangian that we looked at into an SU6 case. And work out the S-wave couplings for omega. Now, there are Hal QCD calculations that indicate the omega system is close to the unitary limit. And what I mean by that is at low energies, you can describe two-particle amplitude with this effective range expansion and just keep the linear term proportional to the inverse scattering length. And so the unitary limit would be taking the scattering length to infinity. And the only way to do this in a consistent way, if you use a particular renormalization scheme referred to as PDS, developed by Kaplan, Savage, and Wise, this would also match a scheme where you use, say, a hard cutoff in when you calculate Feynman diagrams. This can only be satisfied if A tilde goes as 1 over mu and B tilde vanishes identically. And as a result, all of the 2-nucleon channels and the 2-delta channels will be in the unitary limit. Now, there is a bit of hand waviness here, right? We know that at the physical pion mass, the delta decays to a nucleon and a pion pretty quickly. But at heavier pion masses, it can become stable, and the nucleon and delta mass difference tends to shrink. So it would be interesting to study, say, the impact of these constraints for the coefficients on on these other scattering channels, right? And there's also been some relevant research based around this notion that say few nucleon systems can be described by a leading order in terms of 2-nucleon scattering in the unitary limit, and then add irrelevant deformations to this theory through the scattering length and the effective range and other parameters from the effective range expansion. And so, if you watch the Star Wars movies, right, then you know that Episode 8 left more questions than it did answers. Right? And in particular, we've seen how the spin flavor symmetry arises in the large N limit. We also have looked at how to use this technique to constrain the CP violating couplings and neutrinoless double beta decay. But all of these things, require a degenerate nucleon and delta state, right? And so far, no modern chiral potentials or phenomenological models. Well, I shouldn't say none. Some of them do include the delta, but the ones that employ large NC constraints tend not to use them. But we also know from other experimental situations that large N ratios for couplings tend to be somewhat okay, right? But what we were able to do in particular to explore the impact of the delta-delta state on, say, 2-nucleon scattering, we were able to take some lessons from the system with maximal strangeness to learn something about the system with minimal strangeness. But then an independent lattice calculation of, say, the omega amplitude, as well as the delta amplitude that's been calculated by Hal QCD would be beneficial, and we think that these SU4 constraints could be useful in sort of guiding some of the analysis. So that's all.
We have more questions.
Slide 18.
18.
Okay, maybe the one before. Yes. So you said it's a 10% deviation going from the first term in M-N and M delta, right? Is that just because you use NC03?
Yeah, so yeah.
That gives you a measure?
So I mean, relative to the leading order, this is 1 over n squared, right? And if you take NC equal to 3, then it's 1/9. And
Why squared?
so this is NC, this is 1 over NC, rather than being order 1.
Okay. And can you go to that table where you had the different forces in your potential and their NC dependence?
Mm.
That one.
This one?
So, So in this potential, what is the VT? That's a tensor force, right?
Yeah, I was wondering.
Yes.
So it goes as NC. What does that come into the central potential?
So these are just additional things. Here we're really looking at this block.
Oh, okay. Yeah. So those aren't actually in there where you provide estimates for them?
Yeah. Well, Kaplan and Mono are.
Do you want anything easier than two-baryon amplitudes to test?
No, that's all I want. But so I think at least the claim from Hal QCD was that omega was pretty easy because it's a single channel problem, and should have mixed with any other channels since QCD conserves strangeness. Their calculation was that 146 NeV times, but it did disagree pretty strongly with another calculation. I think maybe Tom Liu was part of.
That one was up at like 493 times.
Yeah.
At that pi mass, if the delta is stable?
At 400, yes. But they're doing omega, which is always stable.
But one of the interesting things also that I didn't really say here is if you take seriously Sebastian, Hans Werner, and Bira, if you take seriously this idea that the leading order EFT should be expanded about the unitary limit, you can do that for NN, and the same results will follow. The only consistent theory, like at heavy pi mass, where you expect the nucleon and the delta to be closer to being degenerate than all the NN and all the delta channels will also be in the unitary order.
I have a question about this slide actually. So why is the minimal constraint coming from something with maximal strangeness? Why not a lambda which has one strange?
Because it doesn't mix with any other states.
So that just makes it easier to count?
Yeah.
Okay.
Now, in principle, you can feed this back into all of those couplings as well, and constrain those amplitudes.
At least you gotta ask me for NC difference in the three calculations.
Is that possible?
Oh yeah, it's just expensive.
One NC2 must be cheaper. It's also different from 3.
Then you only have bosons. You don't have any fermionic matter. I think the large NC stuff mostly always, correct me if I'm wrong, assumes odd number of colors when they talk about variance, just to simplify.
Yeah, that's true. Yeah, odd and large.
Yeah.
You can also do some funny things like putting the quarks in the different representations.
Yeah.
Right, you can put like a quark into a 2-index representation, an anti-symmetric representation, and that world is significantly different from this, from what I understand, or from what I remember at least.
All right. I see no other questions. So we all know where to find Thomas most of the time. So thank him again.